All right, Huskies. Afternoon. This is Mr. Goodfellow one more time, and we're going to cover probably, if I was going to say, the most important lesson of Chapter 11, maybe probably the most important lesson of your math career in general. Now, I know that's a pretty broad statement, but for some of you guys, you will probably see this in either one of two different ways. One, you're the kind of math student that just likes to be somebody who can follow directions and you just do what your teacher tells you and you just do it, and that's the way you do math. And then there's going to be a percentage of you guys that really have a whole different idea about this, and you want to understand the whole idea of why. And people who really can ask the question of why really do get a deeper understanding about what I'm going to talk about next, and where you're going to transition from being just a follower of mathematics to being somebody who really truly seeks out to understand the truth about mathematics. Now, before I go down that road, I know that seems really far-fetched and out there a ways. It'll start to sink in a little bit later about what I'm trying to accomplish. Now, before we do that, and make sure that our brains are on fire today, we are going to do the review question to start out with today. This goes over some stuff that we learned in 11.3 and 11.3a, which is about finding out whether or not a function is continuous or discontinuous. Now, just as a refresher on that, I'm going to go over this question, not pause and see if you can do it, but I'm going to do it right now. And we're going to see whether or not this guy has any discontinuities that we would expect. Well, as we discussed yesterday, you usually look at the breaks of the stepwise to make decisions of discontinuity locations, and one of them is probably going to be at a equaling -2, or we might have a situation where it's at a equaling 1, because those seem like the two zip together locations for this piecewise. Now, if I try at -2 and I try my three rules of continuity, we're going to try first to see whether or not f of -2 exists. And f of -2 would trigger the middle one, and -2 negative would be positive. Plus 2 would be 4. And we get an answer for the first step. So we're all right. That domain does exist. Now we'll check to see if the limit as x approaches -2 of f of x exists. And we'll try a left and a right here, because a piecewise is going to definitely be left to right. -2 squared is going to be 4. We've already done the middle one, which is 4. And the answer to the both would be the number 4. So it passes step 2, meaning that the limit exists. And then last but not least, 4 does equal 4, meaning that step 1 and step 2 equal each other, and those are true. We would be able to say that this is definitely continuous at this particular location. All right, so basically that parabola and that negative sloped line would connect at that particular spot of domain at -2. Now, would that be true at 1? Well, let's see here. F of 1 happens to be triggering the bottom one, which would be the number 3. So we pass step 1. Step 2 would be to check to see if the limit as x approaches 1 of f of x exists or not. And if we try that, we would use the middle and the bottom. Well, the right-hand limit would be 3, of course. We did that. The left-hand limit would be -1 plus 2, which would be 1. And we've got a discontinuity right here, is that they do not end up making a particular value, and the limit doesn't exist, so they would be discontinuous at this location. Okay, now that stuff that you guys have been doing right there is a perfect example of what I'm saying is that you like to follow. You like to follow in information and understand how it works just by following somebody's lead. But the question that you really should be asking is, why are we talking about limits? Why are we talking about discontinuity? And where is it all ending up leading us? Okay. Now, in a lot of ways, I like to think of this particular concept as it's really kind of vague. And what I mean here is we're going to check out a little video. Okay. Now, this video, you'll probably laugh at the beginning of it, and I don't know what to expect. But in a lot of ways, your math teachers are acting like one character in this clip, and you have been acting like another. So enjoy the 3-minute clip. It'll be fun to watch, and you'll get some enjoyment out of it. Now, it's a really dark film, and you can't really see real well what's going on right there. So what I'm going to do here is turn up the sound quite a bit so you guys can get it. And you're right, it's from Karate Kid. Now watch this scene, and we'll make a connection to how this relates to math.
Move my arm, all right? What are you doing? What are you... Ow! Ow, what are you doing?
Now show me. Sand the floor.
How did you do that?
Shut!
Sand the floor.
Hey, stand up. Show me sand the floor. Sand the floor. Sand the floor. Big sucker. Sand the floor. Sand the floor. Yes. Now show me wax on, wax off. Hey.
Wax on, wax off.
Wax on, wax off. Hey, wax on, hot. Wax off. Concentrate. Look at my eye. Lock the hand. Thumb inside. Wax on, hot. Wax off, hot. Wax on, hot. Wax off, hot. Wax on. Wax off. Show me penta fence. Up, down. Up, down. Up, down. Other side. Look eye. Always look eye. Show me paint the house. Side. Lock wrist. Side. Yes. Show me wax on, wax off. That! Show me paint the fence. That! Show me side to side. Show me sand the floor. Oi. Hey, look eye. Always look eye. Come back tomorrow.
Okay, you're probably saying G has finally lost it and he is off his rocker. Okay, well, that may be true, ladies and gentlemen, but there's something to be said about the analogy that you're seeing inside this video. And the reason why I show it to you is because it really does show a couple of things that you really haven't seen, and you don't understand is happening in the background. Number one, just kind of breaking down the video itself. There's some things that you're seeing there. First off, you got to decide who you are in that video. And I'm sorry, you guys are all Daniel-san, and your math teachers are Miyagiing the crap out of you. Okay, we have been making you do stuff, and you don't even know why you have been doing it. So if you think about most of your math career, there has been a lot of stuff that's been about repetition. Okay, and that is exactly what Daniel-san does in the video. There's so much repetition of sanding the floor, painting the fence, and so forth, that he doesn't understand why he's doing it. It's basically the same thing that's been going on in your math career. You've been told to do stuff. You've been basically doing it just repetitively over and over again. And hopefully you've had a Miyagi that somewhere along the line doesn't stop with the repetition, but has taken those ideas that you have learned and he's learned how to make them refined or had some kind of refinement. If you're at this level, you're not a person that doesn't know how to factor. You're not a person that doesn't understand that when you do the vertical line test, it's deciding whether or not something is a function or not. You have done it repetitively enough, and then been refined on it well enough that you understand the concept to it. That's what he's refining, the techniques of what's going on. And then you're basically like, I don't really understand what's going on or why I'm doing it, because there's been really no real connection between one set of math and the next. I mean, why did you learn geometry in the middle, and then algebra 2 is on one side of it and algebra 1's on the other, and pre-calculus has got trig in it, and then it's got pre-calculus? Like, what's the connection? How are these things all going together? And then number 4, what happened is that you guys have practiced so much that you've basically built exactly what Daniel has, and that is muscle memory. Okay, and now muscle memory may not, in this case, is about how his arms move and how he learned karate. Okay, karate is your guys' muscle memory is about what you've learned in terms of how the math works in your brain. And when we start doing a lot of this calculus, you're going to have to rely on some of that muscle memory. And if you haven't practiced, then you'll lose the idea of what that muscle memory really is about. Now, throughout the clip, Miyagi also points out that you should always look at eye. Okay? Look at eye really does have its own kind of message to be stated in its own right. And that is, people, learn how to focus. Stay focused on the act at hand and don't lose sight of it. You got to keep shooting for the goal and don't turn and be distracted by something else. And then last but not least, and this is exactly what will happen when you take calculus, is that you will learn all these things that are going to come out, and then in the end, you will have exactly what Danielson has, and that is bewilderment. You will end up walking away going, what the did I just learn? And this happens a lot in calculus. People that walk out of Mr. Motara's class next year from calculus will walk out with the stunned visuals on their head, and they just can't even understand what they just learned because there's so much bewilderment. And the key is don't lose focus on it and use your muscle memory to keep yourself going. Now, I'm going to give you an example of this because we're going to really tackle some ideas when it comes to doing calculus. Now, this calculus that we're going to list over here is going to be about me Miyagiing you about the idea of learning how to do a derivative. Okay, now derivatives happen to be an amazingly large part of what you guys do in calculus. So let's explain where it comes from, because I am not a person to show you just follow me. I'm going to show you why it turns out the way that it actually does. Now, if I was going to connect two lines, it says, could we find the slope of a line that connects two individual points? Well, first thing you would probably say is, yeah, gee, I can find M. That's not really a hard deal because I've done it so many times repetitively and refined it and don't know why it's really that connective. I could totally do it. You know, like y2 minus y1 over x2 minus x1. Okay, now you're right. That particular deal right there is just finding the slope of that red line that goes between these two individual points. Now, if we remember anything from geometry, if it touches 2 points on the same function, it's referred to as a secant. Okay, there you go. There's your geometry connection. And the idea of it being a secant is just the fact that it touches twice. Now, that secant line that we discussed right here, what if it actually changed and instead locked right here at 2.2 and 1, but then it backed up to 6 and 4? So I went 6 and 4 and I connected it right there, and this became the secant line right there. And I basically backed it up a little bit. I'm like, okay, I can calculate the slope of that secant too as well. And then what if I kept backing it up along this particular graph and I backed it up to this point right here, 4 and 2, and I made a line that was like this, and it was still a secant that was going on there. Now, each one of these secants, as you're probably noticing, as they start to move down this deal, they're moving closer and closer until they get so close they're actually on the point, and that line would no longer be called a secant, but this green one would be only touching just the point where it is on the graph at 2 and 1, and that would make it a tangent to the line. Now, this particular tangent that you're doing is super important. It's basically the concept of what derivatives are about. Okay? Now, I'm going to say, why would you even bring up all this stuff? What are you really doing? Well, by shortening this guy back, and this one back again, and this one back again, and approaching closer to 2.1, I'm technically taking the limit as h approaches a. I'm trying to say it's getting really super close to that one singular point, and we're getting really, really close until ultimately it becomes the tangent. Now, you're starting to see, oh, there's a connection. Maybe limits have something to do with derivatives. Now, to put that in a frame of reference, I'm going to draw a little deal here that is about the slope. So we're going to consider the actual, in general terms, what slope is. Now, you wrote up above that slope was y2 minus y1 over x2 minus x1. Great. This is what you learned in Algebra 1. You were repetitive. You had no idea what the connection was. Whoop-de-damn-do. Okay, we can all do it. Now, what I'm going to say is how is that related to as I shorten the secant down till it becomes a tangent? Now, can we all agree that the coordinate down here in the bottom where 2 and 1 was would actually be the domain amount of whatever we're going to be at? In this case, it was 2 over, right? And then if I wanted the range of it, it would be whatever a would be plugged into the function would give me the y value, because y is equal to f of a. All right, so can we all agree that that coordinate would be a and f of a? It's just another way of saying x and y. All right, but that's where that coordinate would be. Now, I'm going to move this guy over a certain amount in terms of domain. Doesn't matter how much I move it. Would you agree that this new location would be a, whatever I started at, plus h more to get over to that spot? That would be that domain value, okay? That domain happens to be the exact same, the one that goes in that spot right there for the x, because it's the x amount moved over. And if, again, I wanted to generate the y component going up to that spot, I'd plug this domain into the function, and I would generate f of a plus h, and I would get the y value. Now, what you've done there is given new definitions of what those two locations could be called. And if I was talking about slope and I was doing slope, it would be y2 minus y1 and so forth down the list. Would that be f of a plus h minus f of a, all divided by, what would that be? A plus h minus a, all right there. Now, all I've done is substitute y1 and y2 and x2 and x1 into the slope formula and generated that idea. And then if I simplified it just a little bit and did a little algebra on it, would you see that the a's would actually cancel each other? I would generate this concept right here, okay? That concept. Now, what's going to happen is this particular point is going to get moving closer and closer and closer and closer and closer until it's actually on top of that 2.2 and 1 concept. Or better yet, I'm going to shorten the h and get it smaller and smaller and limit it out as it approaches 0. Okay, you see this right here? This right here is the definition of derivative. This is a derivative formula. Okay, and that's what you're really finding is what's called the instantaneous rate of change, or better yet, what's also referred to as the slope of the tangent line. Okay, slope of the tangent line. Line right there. Okay, that is by definition the derivative. Okay, now just like in anything math related, we don't learn how to do one thing without learning how to undo it. And a lot of calculus, and there's a great word right here, calculus is about learning how to actually find a derivative. That's calculus A and B. And then later you learn how to undo that derivative, and you learn how to integrate, and you learn how to find an integral, okay, which is basically called an antiderivative, okay? And that is what calculus is about learning what these two things do. Now you're like, why do I want to learn about derivatives? What do they do? And the funny thing is that derivatives in general have so many applications, it's absolutely insane. This particular derivative or slope of the tangent line really represents a lot of things that happen in physics. Things like velocity or acceleration can be talked about, or even position of where something is at, okay? And then that undo, the integral concept, can help you understand area and surface area and volume of certain things too as well. So everything you've been talking about in terms of all these functions can be relatable of what is happening at any one instantaneous point along that graph. You remember that calculus is really the discovery and study of two really aspects. Number one, what's happening at the spot that I'm at right that moment with that domain, or what is happening when I get closer to infinity or negative infinity. And calculus loves to expand on those two topics, okay? Now, on the second page, what I'm going to do up here is I'm going to write down what the derivative is again. Now, they use this symbol right here for the word derivative. It's a prime that you'll see here. You can take second and third derivatives too as well. We'll talk about that a little bit later. But the derivative, by definition, is the limit as h approaches 0 of f of a plus h minus f of a, all divided by h. Okay? Pretty easy concept, and that's the formula it's going to show you. Now, what we're going to do here is we're going to show you how you would have to go through these kind of problems to figure out what's called the slope of the tangent line. Now, what they're asking for is they're saying, hey, what is the slope going to be on this parabola? Let's just kind of maybe make a sketch of whatever that parabola is. I have no idea what it looks like. But if I was going to say the parabola looked like this, and I had this point right here, which is at 2 and 6. That's the location we're trying to find. You're trying to find what is the tangent line doing right there on that particular graph. What's the slope it's given at that instantaneous point. Okay, now you can't just plug it in and get an answer. It doesn't do that stuff for you. What you have to find is the derivative of this particular function. Now, what that derivative is basically saying up there is it says go find the function f and plug into it a plus h. Now, you could replace the a with x. That doesn't make any difference. It's just the domain in this particular respect. So it'd be really f of a is what they're going to say here. So that's really x as well. So what I'm going to do in this top part is I'm going to take this function that's right here, and everywhere I see x, I'm going to put in x plus h. So I'm going to go x plus h, quantity squared, plus x plus h. And that takes care of this very first part right here. And then it says minus from that concept, and we can extend my line out here, minus from that the function itself again. In this case, not plugging in anything extra, but just plugging in x. So it'd be minus x squared, I'm going to put a parentheses around this, plus x away from that deal, all divided by h, and I'm going to take the limit as h approaches 0. Now, you're probably like, okay, awesome, I can just evaluate the limit. And the problem with that is that you can't. Look, the limit has an h on the bottom, and if I approach it equal to 0, the 90% rule doesn't work. So what we're going to have to do is we're going to have to do a little simplification to figure this out. And this is why you took algebra before you took calculus. Because if you don't get it, it's because your repetitive nature isn't good enough. Your muscle memory, el succo. Okay, blame your Miyagi in the past. 2xh plus h squared. I'm foiling this piece right here. Plus x plus h. That's this guy right here in the middle. Minus x squared minus x. Don't forget to distribute across this entire thing. Divided by h. Now, some things will happen here, and they should. because you'll get some cancellations. Look, positive x squared minus x squared, gone. A positive x, a minus x. Bye-bye, see you later. And then you got all these little h concepts that are left over here. Now, here's how I'm going to make this h concept work better for me. Could I steal an h out of all of this? Yeah, you can. If I took the h out, I'd get 2x plus h plus 1, and then that would be divided by h, and I'd be able to cancel it now with the h down there at the bottom. Now, we're very close to this whole thing. It's very easy to forget that the limit is what's taking place when it comes to the derivative, and I want to take the limit as h approaches 0 now must result on the 10% rule. We did the 10% rule. Now I can do 90 on it, and that answer would be, oh, that's a 0. 2x plus 1 is what I would end up with in the end. Now, this answer right here is the answer to the derivative. Now, what the derivative is giving you is it's giving you a formula that allows you to find the slope at any given point on the original function. So if you were to pick any point along that function of x squared plus x, and you plug that domain into the derivative would give you the slope. So if I actually figured out the derivative of 2 on that deal and did 2 times 2 plus 1, and I'm picking 2 because it's the domain on the original function, it would tell me that the slope at the slope of the tangent line at x equaling 2 is the number 5. And that is the slope of this line that's in the blue right here. This line's slope is 5 at that particular spot. Okay, now that doesn't seem like you worked really hard to get that particular answer. But what you'd be experiencing is like this. Like, say this was your roller coaster again, and you were just taking a moment of time, like you snapped a photo of yourself experiencing the bottom or the upside of that roller coaster, and you snapped it on a photo. You could say that if you knew the graph of that roller coaster, you could say at that spot I was experiencing 5 in terms of velocity. And that's what you would be able to say. If you took its second derivative, you could figure out what acceleration you were doing. So the connection here is that a lot of this calculus works hand in hand with physics. And that's why you usually take physics and calculus at the same time. Now, we're going to try a couple of these together to see if we can figure them out. And again, follow along with me as I do some of these derivatives. So it says, hey, find the slope of the tangent line and then get the answer from that and find out what there's a slope-intercept equation of the tangent line. We might have to figure out what that means at the end. Okay, now let's see what we come up with. What is the derivative going to be? Well, it's the limit as h approaches 0 of, now you have to plug in x plus h wherever you see the x. So this is going to be 2 times x plus h, quantity squared, plus x plus h minus 2 minus the entire function again. So make sure you're following the deal. That's minus 2x squared plus x minus 2 all divided by h. Now, again, we can't just use limits to figure this out because the 90% rule doesn't work. We need to do some simplification. So let's see what we got here. 2 times x squared plus 2xh plus h squared plus x plus h minus 2 minus 2x squared minus x plus 2. So I did a bunch of things there. I FOILed some stuff. I distributed the negative through the trinomial. I'm gonna leave the h off for just a second and go 2x squared plus 4xh plus 2h squared plus x plus h minus 2 minus 2x squared minus x plus 2 all divided by h, and the limit as h approaches 0. Okay, now it's still messed up. I mean, the derivative still doesn't work, but you do get some cancellations. Look, 2x squared, those two guys are gone. Maybe an x and a negative x. Bye-bye, see you later. Ooh, was there a minus 2 and a plus 2? Bye-bye, see you later. Have a nice day. Okay, now let's see what our limit is looking like now. As the limit approaches, h is approaching 0. Maybe I could take an h out of all of that upstairs stuff, see if I can cancel it with this h downstairs. So h times 4x plus 2h plus 1. And then if I cancel the h's and apply my limit, I think my derivative is 4x plus 1. Okay, now that formula right there is the derivative formula for any domain that's on that previous function. So let's say, what is the slope going to be if I figured it out? If I figured out the derivative of 1, that comes from the domain of the original 1 at 1, and I would come up with an answer of the number 5. Okay, there's my slope. Wow, that was awesome. Super easy way to do it. Now you answered the first part. What's the slope of the tangent line? Now the next part would be, now you got this graph, you got this line that's got a slope, whatever it happens to be, like this. You know that its slope is 5, but the question is where does it intersect the y-axis? And maybe could I write a y slope-intercept equation for it? Well, slope-intercept comes from point slope. And here's the cool thing about point slope. You need a slope. Hey, got one. You need a point. Hey, got one. I can use point slope. Y minus y1 equals m times x minus x1. There's your point slope formula. Or y minus 1 equals 5 times x minus 1. And then ultimately, those are the ones from the point. If I distribute and write the slope-intercept, it'd be y equals 5x. That would generate negative 5, but then if I added 1, I'd get minus 4, and that is the slope-intercept equation for the tangent line that touches that graph. Okay? You're like, whoa, calculus looks like a lot of algebra. No joke, man. There's gonna be some algebra in there. You've been refined, you've been practiced, it's muscle memory by now. Okay, now you're probably thinking, gee, is there going to be easier ways to do this? And the answer is that calculus, it can be simplified down to some specific plans. I'm giving you a general definition. Those general definitions, it can apply to all of them because the definition is closed on everything. It works. Will there be other plans for other kinds of things? Yes, I will explain that in 11.4a on maybe shortening some of the sequence down. But right now we need to practice the larger piece of the puzzle. As Miyagi would say, look-a-eye. You got to make sure you look-a-eye on this question, okay? Now, some of these can get to be a little bit challenging, specifically if the function gets to be kind of fun. So it says find the slope of the tangent line. All right, find the derivative. Get that in your mind sooner than later. When you see slope of a tangent line, you're just like derivative, derivative. You just got to say it 1,000 times before you got it. But let's find the derivative of this as the limit as h approaches 0 of f of x plus h. Well, that would be the square root of x plus h would be the first one, minus the function itself, the square root of x divided by h. Okay, this is a, oh man, I can't plug in 0 concept. I've got to use some 10% rule. And since you can't really do any foiling and stuff like that, what I'm going to use here is a big old multiplication sign and use one of those techniques we haven't done in a while, and that's conjugate the numerator. X plus h plus the square root of x and square root of x plus h plus the square root of x. And I'm conjugating the numerator because that's one of our 10% rule techniques. And the top, since it's a difference of squares, and that's not something new to you, would end up being x plus h for the first guy and minus x for the last guy because the inside-outside would cancel. And the bottom would end up being h times a square root of x plus h plus the square root of x. I'm not distributing that because that looks like a pain in the pazooter, okay? And I'm going to cancel out my x's. Hey, look, this h is on the outside. That one's on the outside. Those would cancel, and I'd end up with 1 over the square root of x plus h plus the square root of x as the limit of h approaches 0. And I would end up with, as 0 was going in for h, I would end up with a function that says the square root of x plus the square root of x, or 2 square root of x. And that is the derivative of that particular equation. Woo! We got a derivative. We're doing calculus now, baby. Okay, now let's find out what is the derivative's answer at 4. And I'd plug it right into the derivative formula, which is 2 times the square root of 4. And that actually would be 2 times 2, which would be 1/4. And that would be the slope of the tangent line at that spot. Now, I'm not going to move on to find the slope intercept. You would use y minus y1 equals m times x minus x1, and you'd pick the coordinate of 4 and 2. Y minus 2 is equal to 1/4 times x minus 4, and then you would distribute it and figure it out. Okay, that's algebra. I know you know how to do it, and if you don't, then go back to algebra. You don't belong here. Oh man, I said that out loud. That's kind of how calculus teachers believe too as well. If you can't do the fundamental math, then you're just a bump in the road. We're going to go right on past you. Catch up. You can do this. Be Danielson. You're ready for the fight. Okay? Now, here we go. Last one. Let's try one more. Here we go. Let's find the derivative of this function. We're going to get something that says 3 over x plus h minus the original function divided by h. That doesn't work in terms of doing the limit as h approaches 0. That's a bad deal. Looks like I'm going to need common denominators. Now follow along with me so you don't get this one. This one needs an x. This one needs an x plus h. Let's see what we got here. 3x over x times x plus h minus 3 times x plus h over x times x plus h, all divided by h. Ooh, that's a really big, ugly pen. Don't like that one. All right, now if I distributed that and combine my like denominators, I get 3x minus 3x minus 3h divided by x times x plus h, all divided by h over 1. Let's see, we get any cancellations? We got that guy to cancel. If this flipped over and did 1 over h as a multiplier, I think this one and this one would cancel with that guy being gone because I flipped it, and I'd end up with negative 3 over x times x plus h. And that would be, and wait, we're not done yet because what did we not apply? Oh, that's right, the limit as x approached 0. What would the derivative turn out to be? The derivative would be, let's see here, as h approaches 0, that's 0, that's 2 times, or x times x is x squared. Oh, negative 3x squared. This is the formula for the derivative of the original function. Now let's evaluate it for the derivative at the number 1, and the actual slope at that particular spot would be negative 3 over 1 or negative 3. And that would be the answer to the slope of the tangent line at 1, 3 on the original graph. Okay, so, whoa, wow, that's some pretty cool math. All right, now the key to this is going back to these fundamentals that Miyagi talked about. Okay, if you're gonna be good at math, you need to find a way to be repetitive. That's why practice is making yourself perfect. Refine that idea and pay attention to what is the answer, not just throwing answers out there, but seeing if you're right, understanding that there is real connections to stuff, build some muscle memory, don't lose focus, and at the end, be bewildered enough to want to come back and learn more, because it keeps going and it keeps going, and you learn more information out of it. So there's a lot to be said here. Very wise man said, look at I, Danielson, you can do it. All right, so be that person and be the person that knows how to get things done.